Definition of equal sets. So let's begin our discussion on equal sets. Welcome to this tutorial on defining equal sets. As you know, in mathematics, sets are really important. They're like fundamental building blocks that we use to organize and group objects together. Think of them as containers holding specific items. Now, when we work with these sets, it becomes crucial to know when two sets are actually the same. It's not always as straightforward as it seems. We need a precise way to determine if two sets are identical. That's exactly what we'll be covering in this tutorial. We're going to introduce the concept of equal sets. We'll explain exactly what it means for two sets to be equal, and most importantly, we'll learn a method, a step-by-step process, to figure out if two given sets actually satisfy that condition of being equal. Voiceover. In the following slides, we'll go through examples to solidify your understanding, and also point out some common mistakes students make when dealing with this topic. So, let's get started with understanding the definition of equal sets. What are equal sets? So let's move on to the core definition of what makes two sets equal. As we discussed in the introduction, understanding this is fundamental to working with sets. This slide states that two sets, let's call them set A and set B, are considered equal, and we write this as A equals B, if and only if they contain exactly the same elements. Now, that if and only if is important. It means both conditions must be true for the sets to be equal. Let's break down what exactly the same elements means. First, every element in set A must also be in set B. Think of it like this. If you find anything inside set A, you must also find it inside set B. And crucially, it works the other way around too. Every element in set B must also be in set A. We need to check both directions to be absolutely sure. If there's even one element in A that isn't in B, or vice versa, the sets are not equal. Now, a really common mistake students make is getting hung up on the order. So listen carefully. It's crucial to understand that the order in which the elements are listed within a set does not matter. Sets are what we call unordered collections. This means that 1, 2, 3 is considered the same set as 3, 1, 2. We'll see this in action with some examples on the next slide, so keep this in mind. We'll be checking if all elements match up, not if they're in the same sequence. Step-by-step explanation. So now let's really solidify this idea of equal sets with a step-by-step example. We'll start with example 1. We have two sets, and we'll call them A and B. Set A contains the numbers 1, 2, and 3. We represent this as A equals the set containing 1, 2, and 3. Set B contains the numbers 3, 1, and 2. Now, remember from the previous slide, to prove that A and B are equal, we need to check two things. First, we need to verify that every element in set A is also in set B. Let's do that. Is 1 in set A? Yes, it is. And is 1 also in set B? Yes, it is. Great. Next is 2 in set A? Yes. And is 2 also in set B? Yes. Finally, is 3 in set A? Yes. And is 3 also in set B? Yes. So, we've confirmed that every single element of set A is present in set B. Excellent. But we're not done yet. We also need to check the reverse. We need to make sure that every element in set B is also found in set A. Is 1 in set B? Yes. And is 1 also in set A? Yes. Is 2 in set B? Yes. And is 2 also in set A? Yes. Is 3 in set B? Yes. And is 3 also in set A? Yes. Perfect. We've now confirmed that every element in set B is also in set A since both conditions are met. Every element of A is in B, and every element of B is in. We can confidently conclude that set A is equal to set B. We write this as A equals B, and importantly, notice that the order in which we listed the elements didn't matter at all. The sets are still equal because they contain the exact same elements. Now, let's look at example 2 to reinforce this. We have set A containing the letters A, B, and C, and set B contains the letters C, B, and A. If you follow the same logic as we did with example 1, checking that every element of A is in B, and then checking that every element of B is in A, you'll find that it holds true. Every element in A is also in B, and every element in B is also in A therefore. Just like before, we can conclude that A equals B. This further emphasizes that the order of elements doesn't change whether two sets are equal or not. This is a crucial concept, and we'll be building on it in the next slides, so make sure you understand these examples thoroughly. Key takeaways. Let's recap what we've learned about equal sets. This slide, titled Key Takeaways, summarizes the most important points. Firstly, it states that two sets are equal if and only if they have precisely the same elements. What does if and only if mean? It means both conditions must be true for the sets to be equal. They can't be missing any elements, and they can't have any extra elements. Think of it like a perfect match. Every single item needs to be accounted for in both groups. Secondly, and this is a really important point we touched on with our examples, the order of elements within a set does not affect equality. Remember in the previous slides, we had sets like A equals 1, 2, 3, and B equals 3, 1, 2. We confirmed those were equal, even though the numbers were listed in a different sequence. Sets are unordered collections, so rearranging the elements doesn't change the set itself. Finally, to determine if two sets are equal, you need to verify that each element in the first set is also in the second set, and that each element in the second set is also in the first set. This is the systematic way to check. Don't just look for similarities, you need to confirm a complete two-way match. Keep these takeaways in mind, because in the next slide, we'll be discussing some common mistakes students make when working with equal sets. Understanding these key points will help you avoid those pitfalls and confidently identify whether two sets are truly equal. Common mistakes. So the first point here says, a common mistake is to assume that two sets are unequal simply because the elements are listed in a different order. Remember that sets are unordered. And finally, the second point states, another mistake is to overlook an element that is present in one set but not in the other. Always carefully compare the elements of both sets to ensure they are identical. Let's move on to the final slide, where we discuss some common pitfalls students often encounter when working with equal sets. This is important because understanding where you might go wrong is just as crucial as knowing the definition itself. Now we've already seen in the examples on the previous slides, like when we had set A as 1, 2, 3 and set B as 3, 1, 2, that the order doesn't matter. Sets are not like lists where 1, 2, 3 is different from 3, 1, 2. In mathematics, we don't care about the arrangement. As long as both sets contain exactly the same elements, they are equal. So don't let a different listing order trick you into thinking the sets are different. Keep in mind that sets are unordered collections. This is about being meticulous. When you're checking if two sets are equal, you need to go through each element in the first set and confirm it's also in the second set, and then do the reverse, check each element in the second set to make sure it's in the first. It's easy to glance and think they look similar, but a single missing or extra element will make the sets unequal. So, take your time, be systematic, and double-check to avoid overlooking anything. That concludes our discussion on equal sets. Remember the key takeaways: same elements, order doesn't matter, and careful comparison. You should now be able to confidently determine if two sets are equal or not.